Hello, we are going to try to solve the problems in the final chapter of Vol3, which is diffractions. And in the diffraction, we need to think about there's a big slit with the size. Then we get a sine theta m lambda for the fringes. So that means there's a central peak, then yes, these fringes, and these fringes will governed by the sine theta equal to m lambda. And then there is X-ray diffraction. So then X-ray is this kind of atomic plane with a distance over d. And then if it is impinged upon the theta, then as a result of X-ray diffraction, for example, 2d sine theta equal to m lambda will be the bright spot. So that it is, you need to know that A is for aperture, single aperture, single slit, and this is the X-ray diffractions. So it is a little bit different. It is the 2D, and that is A, okay? So now let's try to solve it. So single slit problem, there is a single slit, and this is the first minimum, and how wide? Try to find out A, okay? So we get that this minimum, the fringes is going to be described by this formula. For the first minimum, m equal to 1 is here. M is going to be 1. Then A sine theta is lambda, and then A is given by lambda over sine theta. And theta is given 28 degrees. And then you can get the A. So basically, it's just a plug-in type of a problem. Okay, and then find the magnitude of angle between the first minima for the two sodium vapor lines, so that we have a lambda 1 and lambda 2. Okay, so lambda 1 and lambda 2. And when they fall upon a single slit over with this one, so that it is a diffraction, but we need to find out the separation of a minimum for different wavelengths. Okay. Theta becomes proportional to lambda, and then delta theta, the angle difference would be proportional to delta lambda over A. Okay, so we get A sine theta is lambda, m equal to 0, and the small angle approximations, sine theta becomes theta, okay, theta becomes this one, okay. For the theta 1 is lambda 1, A over A, theta 2 is lambda 2 over A, delta theta is just delta lambda over A. And then you get the delta lambda is given by this one, lambda 2 minus 1 is this much, and then delta theta is this much, okay? Or you can just plug in from this value without any these approximations. You can get the theta 1 is arc sine of this one. Theta 2 is arc sine of this one. And then from this, you can get the same, more or less similar one. But you will find that that is a little bit different. So if you take the arc sine, then you will get this number. So monochromatic light over wavelengths incident on the double slit and the unknown separation result in a diffraction pattern containing 5 interference peaks inside a central minimum. Find the separation of a slit. It is the is a combination of interference and diffraction. So what we need to find out is the slit width is given, and then we need to find out D, separation of these slits. Okay, so for the interference maximum condition is given by this one. Diffraction minimum condition is this one. Okay, this one. And we need to find out the visible peaks. So here is the case. We have seen it in the lecture. And interference is this, diffraction is the blue line, and altogether you get this one. Then you get peak 1, 2, 3, 5. But in this case, there is a missing order m equal to 3. So m equal to 1, m equal to 2, m equal to 3. So it is a missing one. So we have to count it is m equal to plus minus 3. Okay. So we, instead of 2, we should plug in 3 here. Okay. So we get d sine theta is going to be 3 lambda, and then a sine theta is going to be lambda for these cases. And then this will satisfy our combined interference and diffraction patterns. And then by doing so, you can get the this condition. D sine theta over a sine theta is given 3 lambda over 3, and the d over a 3, so that slit spacing is given by 3 times a. Okay, that's the outcome. So key point is that you need to put the 3 here because it is a missing order. Okay. When a monochromatic light wavelength 430 nanometers incident or double slit, separation is given. There are 7 interference fringes in its central maximum, and how many interference fringes will be the central maximum over light wavelengths over 332.8 nanometer for the same double slit. So we have 7 interference fringes for a certain wavelength, lambda 1. And then the question is, how many fringes for the lambda 2? For the same double slit. So that means the separation of the slit is the same, and the slit width is also the same. Okay. So interference maximum is given by this one, and the diffraction minima is given by this one. Okay. So in this case, what is happening here is that with this theta, you get the interference maximum, and then in this theta, you get the minimum, okay? And then boundary of the central maximum is given by this value. And the substitute into the interference condition, and then d sine theta, okay, so we get this number. And then you get d sine theta is given by d over a. I think that this is wrong. Okay. D sine theta, d sine theta here, sine theta has been changed into lambda over a, so that it should be lambda. Oh yeah, I'm sorry. Sine theta, okay, sine theta is given by m lambda over d. And the sine theta is given by lambda over a. So these two should be equal. Okay, and then as a result, you got m equaled d over a. Okay. And the number of visible fringes, including missing orders, we have talked about it. So N1 was the 7, okay? And then we get, this is the M, missing order, counting the missing order. And then there is then you get the 7, okay? So that what we get is D over A is 4. And then what we have going to do is that for the another wavelength, this is for the lambda 1, and this is for the lambda 2. And then we are going to apply the same rule because we are going to have the same D and A parameter. And the D over A does not change. And as a result, number of fringes does not change. So what it means is that if you have a certain slit, two slits with a certain slit separations, and then also slit width, the number of fringes is not going to change if you change the wavelength slightly. But what it changes is that its dimension. Dimension is going to change. The pattern does not change. Pattern is not changed, but only the dimension, actual theta is going to change. Okay. 85, an X-ray scattering experiment is performed on a crystal whose atoms form a plane separated by this one. This is the D, okay? What is the angle at which experiment needs to illuminate the crystal in order to observe the first order maximum? And we know that this formula, Brock's law, first order n equal to 1, then you get this relationship, and then solving for the theta, you get this one, okay? So this is a direct plug-in type of problems. Okay, and then another X-ray diffraction. So we have an X-ray. So we have an angle is given, and then we are not known for the wavelengths. Lambda is not known. And then determine the spacing between the reflecting plate, D. So first case is the theta 1 is 27.1. And the second case is we have a known wavelengths, but we are going to have a m equal to 2, okay? So following the Bloch's law, 2D sine theta equal to m lambda, and then for the unknown, for the known wavelengths, we have this one, okay? So that d sine theta 2 equal lambda 2, so that we find out the spacing, okay? So d is known, now known. And then what we are going to do is that utilize evaluate the sign here, and then you get D, okay? And then once again, let's try to find out. I think that, yeah. In this case, what we need to find out is that the unknown wavelengths, okay, unknown wavelengths, and then we utilize the Brock's law, and the second case to find out what the D is, because in this case theta 2 and the lambda 2 is known. From the theta case, second case, we find out what the D is, okay, and then use the first case to calculate the unknown wavelengths. Theta 1 is known, now D is known, and then lambda 1 can be found, okay? First order Bragg angle for certain crystal is this angle. What is the second order angle? Once again, we are applying the Bragg law to the sine theta is m lambda. First order m equal to 1. Okay, second order relation m equal to 2. And then if you just arrange it, sine theta 2 over sine theta 1 is 2. So sine theta 2 for the second order is given by 2 sine theta 1. And then if you just plug in what the theta 1 is, and then you can find out theta 2 in degree, and then you should change it into the radian. Okay. And thin film of soap coats a piece of a flat glass. How thick is the film if it reflects 395 nanometer? Light most strongly when illuminated normally by white light. Okay. So in this case, once again, we are going back to 75 problems. Somehow I think that we have done it before. So in this, what the key point is that soap on a flat glass. So that it is N1, 2, and 3. And then there is a a 5-phase shift here, and then another 5-phase shift, so that it pi plus pi is 2 pi, so that means that there's no relative shift, okay? And then you utilize the constructive relationship, and then you can find out what the t is. Okay, thank you. It's been a pleasure to work to have a class with you, and good luck with the exam 4.